Okay, today we're going to be looking at the topic of binomial coefficients, but before I get into that, we're going to be looking at something called a factorial and what that means. So to access the topic of factorials, we're going to consider how many ways there are of arranging n objects. So let's start with n is 3, and I've got three colours there, red, green and blue. And we're going to look at how many different ways there are of arranging these three colours. So I've got red, green, blue, that's obviously one way, but what I could do is I could just swap the green and the blue around to give me a second way. So that's two ways. I could put green out the front, so green, red, blue, and then of course I could keep the green out the front and then swap the red and the blue. So that'll be green, blue, red. And blue's not been out the front yet, so I could put blue there, and then I could put red next, and then green, and then of course I could keep the blue at the front, and I can swap the red and the green. So this gives all the possible combinations or the possible arrangements of these three objects. And this says that there are 6 ways. There are 6 ways to arrange 3 objects. Okay, 6 ways to arrange 3 objects, and that's all 6. You can't do anything else. That is comprehensive. Okay, so how do we get from 3 to 6? Well, let's look in a bit more detail as to exactly what's going on here. So I've got n is 1, 2 and 3 all laid out. So if you have one object, then clearly there's only one way to arrange it, and that is just by itself. If you have 2 objects, then you can have the first one first, second one second, and then you can swap them around. So that's 2 ways. And as we've already seen, there are 6 ways to arrange 3 objects. But what I want to draw your attention to is kind of this bit here, because that looks like one of those. This bit here, because that looks like one of those. And then this bit here, which actually that one is one of those. And what you'll notice is that each time you go up by 1, or increase n by 1, you are applying the previous one n times. So in this case, we are applying the previous iteration 3 times. This is here, you're applying the previous iteration, green and red. The previous iteration, you're applying that one twice. So here you're applying this one 3 times, and to forget this one, you're applying this one twice. So if we want to get to n is 4, and we want to add a 4th colour, say pink, all of that can be pink. And then what we would do is we'd swap the pink in for a red and draw the red out, and then repeat that pattern. And then we could swap the pink in and take the blue out instead. And then finally we could swap the pink in and take the green out. So we've got 4 of these. So each time you go up by 1, you are actually multiplying by n. And this is exactly what a factorial is. You are multiplying by the previous number. So n, if n is 1, then there's 1 way to do it. If n is 2, there's 2 ways to do it. If n is 3, there's 6 ways to do it. If you add a 4th colour, I've added pink, then there are 24 ways to do it, because you're doing the previous one times 4. The next one would be the previous one times 5, so that's now 120 ways to arrange 5 colours. And in general, we would call this n factorial, which we denote with an exclamation mark. Okay, n factorial. Okay, that's a general case. By definition, n factorial is equal to n times n minus 1 times n minus 2, and you keep going until you get down to the number 1 and you stop. Okay, that's the definition of n factorial. This is true for n is a positive integer. there is one number we haven't tackled yet, and that's this empty space here. It's important that we define 0 factorial, and there are a couple of different ways that we can argue this point. Number one, I'm going to say 0 factorial is 1 because there is exactly one way to arrange no objects. Okay, there it is. Okay, one way to arrange no objects. Okay, there's no objects in there, that's the only way I can arrange it. An alternative way to view this is to say, well, to get from here to here, I divide by 5. To get from here to here, I'm dividing by 4. Here to here, I'm dividing by 3. Here to here, I'm dividing by 2. So I should then, if I follow that pattern, I should divide by 1. And of course, 1 divided by 1 is 1. So it's important to note that we define 0 factorial to be the number 1. Okay, so that's factorials. Let's have a look then at the binomial coefficient. Well, what is a binomial coefficient? Well, binomial coefficients we're going to be using in binomial expansions, which I'm going to do in a separate video. Today we're just going to be looking at the binomial coefficients, which is asking the question, how many ways are there of choosing R objects from N? Okay, I'm going to write that down. How many ways are there to choose R objects from N? Okay, that's the question that binomial coefficients is asking. How many ways are there of choosing R objects from N? Okay, well, I've got 4 objects here. Okay, I've got red, blue, green, and pink. Let's say I want to choose no objects. Well, there's one way to do that, and that's to choose no objects. Okay, that's simple enough, isn't it? Okay, if I want to choose one object, well, I could choose just the red one. So I could just choose red. Or I could just choose blue. Or I could just choose green. Or I could just choose pink. So there are actually 4 ways I can choose one object. So I've got 4 ways over here. Okay, what about 2 objects? Well, I could choose red and blue. So that's 2 objects. Or I could choose red and green. Okay, so that's another pair. Red and green. Or I could choose red and pink. So red and pink. Can't do anything else with red. Okay, well, I could select blue and green, I suppose. So blue and green. Or I could select blue and pink. Blue and pink. And then the other pairing, which I haven't done yet, is green and pink. Green and pink. What's important to note here is that the order that I choose them doesn't actually matter. So choosing red and blue is the same as choosing blue then red. Okay, it's just the number of pairings I want to take, not the order of the pairings. So I've got 1, 2, 3, 4, 5, 6 ways to choose 2 objects from 4. Okay, what about 3 objects? Well, this seems to be getting bigger, so I'm expecting more than 6 perhaps. All right, so red, blue, and green. Okay, that's one way. Or I could choose red, blue, and pink. Okay, so red, blue, and pink. Or I could choose red, green, and pink. So red, green, and pink. Or I could choose blue, green, and pink. Blue, green, pink. Yeah, well, that's only that's only 4 ways. And if you think about it, that actually kind of makes sense. Because the number of ways of choosing 3 items should be the same number of ways of choosing 1 item. because instead of choosing one of these four, I'm choosing one of these four to leave behind. So this one I've left behind the pink, so that's the same as that. This one I've left behind the green, so that's the same as that. This one I've left behind the blue, so that's the same as that. And this one I've left behind the red, so that's the same as that. So actually it makes sense that there's 4 ways to choose 3 from 4. And then finally, if I want to choose 4 items, well, I'm leaving none behind. So surely there's only one way to do this, and that is to choose all 4 of these objects. Red, blue, green, and pink. So there is one way. So that's with n is 4. 1, 4, 6, 4, 1. That is a row in a very famous triangle. It's exactly what we're going to move on to now. This triangle is referred to as Pascal's Triangle. And there we can see our 1, 4, 6, 4, 1. Now the way the Pascal's Triangle is defined is there's 1s down the 2 edges, and all the elements inside the 1s are equal to the sum of the 2 numbers directly above it. So in this case, the number 3, for example, is equal to 2 plus 1. Or the number 35 here is equal to 20 plus 15. Or the number 28 over here, that's equal to 21 plus 7. Okay? So that's exactly how Pascal's triangle is constructed. And within Pascal's triangle, there are loads and loads of patterns. For example, we have the trivial pattern 1, 1, 1, 1, 1, 1, 1, 1, 1. But if you look down this row, we've got 1, 2, 3, 4, 5, 6, 7, 8. We've got all the integers. Down this row here, we've got what's called the triangle numbers. So 1, 3, 6, 10, 15, 21, 28. Okay, they're the triangle numbers. And each of these actually creates its own pattern. Or we could look at the rows. So that sums to 1, that sums to 2, that sums to 4, that sums to 8, that sums to 16, 32, 64, 128. And if you add those numbers together, they sum to 256. You see the powers of 2. And one of my other favourite sequences is also in here. If you take an oblique direction, 1, 1, 2, 3. If you sum those 3 numbers, you get 5. 1, 4, 3, that's 8. 1, 5, 6, 1, that's 13. This actually creates the Fibonacci sequence. So within Pascal's triangle, we have the Fibonacci sequence at a bit of an oblique angle. And of course, you can carry that on. And I'm sure there are many, many other patterns in here that I don't even realise. But it's a very easy, simple definition to work with, but yet there's so much hidden mathematics in it. It's fabulous. So what I'm going to do is just going to take Pascal's triangle, and I'm just going to kind of push everything over to one side to create for myself a kind of right angle Pascal's triangle. It's still Pascal's triangle, it's just so I can easily reference each number. And what I've done here is each row is I've assigned an n value to it, and each column I've assigned an r value to it. And we can see it's obviously still Pascal's triangle. So we've got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So that's the line we were looking at on the previous page. 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. And it continues onwards. The notation we use is NCR. Okay, superscript N, big C, subscript R. That's the notation I use. You may also see the notation NR written as a column vector. I'm not such a fan of that one, as it looks like a vector. And occasionally you can see NCR, which is also a notation that's used in some literature, but you will catch me writing this most of the time. Okay, NCR. And it's defined as the number of ways of choosing R items from N. Okay, so if we have 4 items and we want to choose 2 of them, there are 6 ways to do it. If we have 6 items and we want to choose 4 of them, then there are 15 ways to do it. And And clearly it is necessary for r to be less than or equal to n. For example, you cannot choose 9 items if you only have 8 to start with. So that's why this half of the triangle is blank. Okay, it doesn't make sense. But some good news for you. You do not need to draw Pascal's triangle out every time you want to calculate a binomial coefficient, because there is a formula that goes with it. And the formula contains factorials, which is why I needed to introduce factorials to you first. NCR is equal to n factorial divided by r factorial times n minus r factorial. Okay, that is the factorial definition of the choose function, also known as the combinations function, or the number of combinations that you can choose. And it gives you all the elements of Pascal's triangle without you having to draw the triangle out. So, for example, if I wanted to calculate 6 choose 4, okay, we can see from the grid that 6 choose 4 is 15, so I'm expecting this formula to give 15. 6 choose 4, well, that's going to be 6 factorial divided by 4 factorial times 6 minus 4 factorial. Okay, that's just me plugging n and r into the formula which I just wrote on the previous page. 6 factorial, well, that's going to be 6 times 5 times 4 times 3 times 2 times 1 as well, but that obviously doesn't change anything. 4 factorial is 4 times 3 times 2, again times 1, but doesn't do anything. 6 minus 4 is 2, and 2 factorial is 2. Okay, so there's that. And what you'll find is there'll be numbers that cancel top and bottom, so 4, 3 and 2 will cancel top and bottom. And then the 2 that's left on the bottom, I can cancel with the 6 to make a 3, and we're left with 3 times 5 with nothing left on the bottom. So that comes out to be 15 as we expected. I'm not going to go into the proof as to why this NCR formula works and gives the coefficients of Pascal's triangle as it does in this video. But there are plenty of resources online which will give you the reason why this works. Okay. Yeah, thank you very much for watching.